We're going to look at now the cancellation properties of these inverse trig functions. Because they're not perfect inverses, we're not going to get perfect cancellation. So we have to be really careful and just look back at the meaning of these partial inverses. So for the first one, we have sine to the -1 of some sine ratio. So your first instinct is probably that you want to just cancel these things and have 7 pi over 6. The problem is 7 pi over 6 is not in that output region for our sine function. So this one's not going to work. So we can't cancel that out. Our outputs for sine to the -1 have to be in there. So what we need to do is figure out what this actually means. So if this is going to be some theta, what this means specifically is that theta should be in that restricted domain of -pi/2 to pi/2, and then it has the property that sine theta equals sine of 7 pi over 6. So it has the same sine ratio, but it's in a different quadrant. So same as always, we can draw this out on the xy plane. To be between -pi/2 and pi/2, I need it to be in the right-hand side, right? -pi/2 up to pi/2. And then what I will do is draw my 7 pi over 6. So that should be pi plus another 30 degrees. So there's this triangle here. And since that is 30 degrees, I know my ratios should be 1, 2, and √3, and both of those are negatives. And so if I were to draw the angle on the other side that has the exact same ratio, my theta in -pi/2 to pi/2 with the same sine ratio, it needs to be the same triangle. So it's going to be drawn over here. I need the y to be negative for my sine ratio to be negative. And so if on the left, if this reference angle is 30, the other reference angle also has to be 30. And so what I get is -30 degrees or -pi/6. Okay, so we would investigate all of these basically the same. The next one, so this is theta in 0 to pi, sorry, not 0 to pi, I'm looking at cosine, the tan region with tan theta equals tan of -45 degrees. So just this interval here is the same as -90 to 90 degrees. And so what we can actually see here is that theta is the angle that's in there. It's actually good. We're good to go. -45 is in that region, so that's my theta. It's that exact one. So I get 45 degrees. And I would actually, sorry, -45, I should say, not 45. I keep this one in degrees because the original question is phrased in degrees, so my answer should also be phrased in degrees. So yeah, so just -45. We actually do get perfect cancellation if our input, that -45, is in the restricted domain. Okay, and finally the last one, just a cosine example. So this is not going to be a special angle for this one, but we don't need it to be to draw those triangles. So same thing, I'm just going to write what this is. I don't have a C here, so I guess I'll put C. So this is theta in the cosine region, 0 to pi. So I'm going to just rewrite that to degrees, since our answer will be in degrees, with cos theta equals cos of -50 degrees. So for 0 to 0 to 180. That means it has to be in the top half of the xy plane. And I want the same cos as -50. So if I were to draw -50, that would come down here by 50 degrees. So my reference angle would be just 50. So in the first example, I labeled all the sides, but if you look at the picture, I didn't need the sides at all. All I need is the same triangle to get my theta. So if I want to get this theta, I just need to draw the same triangle that has a positive cosine. So it's going to go in the right-hand region. Same triangle, so I get all the same ratio. So it has to have the same angle. So the reference angle is 50. And that means that that is actually my answer. It's the 50 degrees. And yeah, that's actually my output. I don't have to do any conversion. So that will actually be 50. And you can try that on your calculator. It should spit out the 50 for you. All I'm trying to do is explain it. So now we're just going to look at the reverse order of cancellation and see what happens here. So for the first one, we've got cos of cos inverse of a half. Maybe again, I'll just rewrite one of these as an arc sine just to make sure you're used to seeing both. Yeah, so cos of cos to the -1 of a half. So just if you're parsing what this actually means here, this is theta, specifically theta in 0 to pi with cos theta equals 1/2. And so what we would actually have here, if I were to find that theta, this would be cos of that theta, right? And we literally just said that that theta is a half. So we actually don't really have to pay too much attention to this. It is a half. That's my answer. So we actually do get this cancellation here, but I'm going to write this definition out every single time because on one of them we are going to hit a little bit of a snag. So in the next one, this is going to be theta in -pi/2 to pi/2 with tan theta equals 4. And the last one, arc sine is just the same as sine to the -1. I just changed it because you should be seeing both of them. This is going to be theta in -pi/2 inclusive to pi/2 with sine theta equals 4. Okay, so hopefully something is kind of ringing some alarm bells here. The tan theta equals 4, that's totally fine. If I look on the graph, tan theta equals 4 would just be like something up here. It eventually would get up there. So there is definitely some theta in there that does this. The cos theta equals a half. We know that happens. That's right about there. Now the sine theta equals 4, this is a problem. That actually doesn't exist. So on the tan one, we're going to get the normal cancellation here. It's actually going to work out, and like by construction of the theta that we're looking for, that actually just cancels. Perfect cancellation. Good, good, good. Unfortunately, though, on the last one, there is no such theta. So there's a huge problem here in that the input does not exist. There is no arc sine on 4 because it's outside of the range of sine. And so we've got a big problem here. This thing doesn't exist. So just in general, we will get cancellation as long as the input is in the range of the corresponding function. But again, you'll be able to figure this out by just plugging these things into a calculator. And for these ones, it doesn't even matter what calculator setting you're in, radians or degrees, because it's the angle is just going to kind of happen in that middle step and get wiped out when you then apply the trig function to that angle. It's going to send it back to the ratio, so it doesn't really matter. So for the most part, these are going to cancel perfectly as long as it's actually in the domain.